Now, the next topic is Laplace transform. So, what's a Laplace transform? Laplace transforms, its input is a function of t, and its output is a function of s, defined by this formula that you see. Well, in other words, maybe let me write some simple equation. So suppose that we want to find the Laplace transform of, say, some constant c1 times f1 of t plus some constant f2 of t, right? So then, by definition, this is the integral from 0 to infinity e to the minus st, and then here I should write the input of the Laplace transform, which is c1 f of t plus c2 f of 2 of t dt. But then, of course, I can take out c1 and c2 and represent this as a sum. So this is going to be c1 times the integral from 0 to infinity e to the minus st times f1 of t dt plus c2 times the integral from 0 to infinity e to the minus st f2 of t dt. And this is c1 times the Laplace transform of f1 plus c2 times the Laplace transform of f2. In other words, what we see is that the Laplace transform is actually a linear transformation from the space of functions in T to a space of functions in S. Well, however, accurately defining these functional spaces is a bit tricky, so I'm not going to get into details here, but the main message is that the Laplace transform is a linear transformation from a infinite dimensional vector space to an infinite dimensional vector space. Please take this message, and now let us go through a few specific examples of Laplace transforms. Right? So, going to do 4 examples. How do we find the Laplace transform of e to the minus 2t? So by definition, this is the integral from 0 to infinity times e to the power minus st times e to the minus 2t dt, which is from 0 to infinity e to the minus s plus 2t dt. Now let us find the antiderivative. So the antiderivative is minus 1 of s plus 2 times e to the minus s plus 2t, and we should take the change of this from 0 to infinity. Well, now if this function, since here we have the change from 0 to infinity, so we need to be able to substitute infinity st, and substituting infinity st means taking the limit of this expression as t approaches infinity. But of course, the limit of an exponential function is finite if and only if the exponent is negative. So in order for this to be a finite number, we must have s must be bigger than negative 2, right? Because if f is smaller than negative 2, then s plus 2 is a negative number, so minus s plus 2 is going to be a positive number, and the limit of e to a positive exponent t as t goes to infinity is going to be infinite, and this is just undefined. But on the other hand, if s is bigger than minus 2, then in this case this is a negative number. I mean the whole thing is a negative number, and then the limit of this is just 0. So in other words, this is minus times minus 1 over s plus 2, and this is just 1 over s plus 2. Okay, so the Laplace transform of e to the minus 2t is 1 over s plus 2. So, by a very similar logic, so the Laplace transform of e to the power 2015t is going to be the integral from 0 to infinity e to the 2015t times e to the minus st dt, which is the integral from 0 to infinity of e to the power minus s minus 2015 t dt. And again, this is minus 1 over s minus 2015 times e to the minus s minus 2015 t, and I should take the change from 0 to infinity. But in order for this change to be defined, this whole thing has to be negative, so s has to be bigger than 2015. But if s is bigger than 2015, then the limit of this expression when t goes to infinity is just 0, and the result is 1 over s minus 2015. Okay? All right, I hope this is clear. So let me do the next thing. Then the next one is going to be a little bit more complicated, but I'm going to cheat. Yeah, I'm going to do integration using Wolfram Alpha. All right. I have actually prepared it in advance, so I'm not going to even refer to Wolfram Alpha explicitly. But so what is the Laplace transform of t squared minus 10t? This is by definition the integral from 0 to infinity e to the minus st times t squared minus 10t dt. Well, now if you kind of want to do it by hands, then you would have to do integration by parts twice here, which I don't want to do, especially, you know, it's very easy to make a mistake, but I hope that you know how to do integration by parts. So I'm just going to give you the answer. So the antiderivative of this is, is e to the minus st times minus 2 over s cubed minus 2t over s squared plus 10 over s cubed minus t squared over s plus 10t over s. And then we should take the change from 0 to infinity, right? So this is the antiderivative of the integrand. Well, and then we should take the change from 0 to infinity. But then notice that when t approaches infinity, the only way for this to be defined, when t approaches infinity, you need this thing to approach 0 as t approaches infinity. So in other words, in order for this to even be defined, s has to be positive. Because if s is negative or if s is 0, then the limit as t goes to infinity is infinite, so that there is this expression does not make sense. Okay, so but if s is positive, then the limit of e to the minus st is 0, and then even the limit of e to the minus st times any polynomial is still 0, because the exponential function, it dominates any polynomial. So the limit is going to be 0. So the change is actually minus the value of this expression when t is 0. And when t is 0, e to the minus st is always 1. So then we are going to have minus 2 over s cubed, then minus 2t when t is 0 is 0, and plus 10 over s cubed, minus 10 over s cubed, minus t squared over s when t is 0 is 0, and 10t when t is 0 is also 0. So this is actually the answer, 2 over s cubed minus 10 over s squared, sorry. Okay, and the last example is the Laplace transform of cosine t. Is again, so this is the integral from 0 to infinity of cosine t times e to the minus st dt. And again, I'm going to use Wolfram Alpha to find the antiderivative. The antiderivative is e to the minus st times sine t minus s cosine t over s squared plus 1. And we should take the change from 0 to infinity. And again, this only is defined when s is positive, because if s is 0, then there is no limit when t goes to infinity. It's just oscillations. If s is negative, then e to the minus st is an exponential function with a positive exponent. If t goes to infinity, well, we're going to have oscillations of increasing magnitude, but there is no limit. So in order for this expression to have a finite limit when t goes to infinity, s has to be positive. But if s is positive, then the limit of e to the minus st at infinity is 0. The limit of the whole expression is 0. So therefore, the answer is the minus the value of this expression when t is 0. Okay, so when t is 0, e to the minus st is 1. Sine of 0 is 0, so cosine of 0 is 1. And the remaining thing is just s over s squared plus 1. Okay, I hope it is clear. So that's this gives you some intuition of what Laplace transform is about. So basically, the input of the Laplace transform is a function of t, and the output of the Laplace transform is another function of s. And then the output is a completely different function. So if the input is an exponential function, then the output is 1 over s minus some number, is a fraction. So another thing is that the Laplace transform, the domain of the resulting function can be, I don't know, the set of positive values of t can be some infinite interval from -2 to infinity, or from 2015 to infinity. Well, but it depends. So there could be different cases here. So here is a definition. So we say that a function f of t is of exponential order if there exist some constants such that the absolute value of f of t is less than some constant times e to the at. Well, when t is sufficiently large. Okay, so and a simple lemma. If you want to prove it, I suggest that you try to prove it and post your proof as comments to this video, but it's not very challenging. So if a function is of exponential order, then the Laplace transform is defined for all s that are bigger than a. Right. So in other words, so it means that, well, clearly all polynomials are of exponential order, with a being any positive number. Right. So any polynomial or any rational function grows slower than any exponential with a positive exponent. And of course, all exponential functions are also of exponential order, and all trigonometric. So in other words, so any linear combinations of exponential, trigonometric, polynomial, and, well, even fractions, they are going to be of exponential order, which means that the Laplace transform is going to be well defined for them. So here is another little theorem for you. So this is a very important property of the Laplace transform. I could prove it, but I